This video is about equilibrium. Now, we've been doing chemical reactions since we've learned them, and this is the same thing. It's just another chemical reaction, but it's done what's called reached equilibrium. So most chemical reactions do not go to completion. Okay, they do not actually complete. But some, but not all the reactants react to form products. These products can recombine to form the original reactants. Okay, so this means literally the reaction can go back and forth. So you get this two-sided arrow. This means FeO is breaking down into Fe plus O2, but at the same time, if it's at equilibrium, Fe reacts with oxygen to form FeO. So you have this sort of going back and forth. In a closed system where matter and energy cannot enter or escape, the concentrations of the reactants will eventually become constant. So this is going to be a key thing here. Concentration of reactants will eventually become constant. Not necessarily equal. Okay, that's not where the equilibrium comes in. The concentrations of the reactants in the products will become constant, meaning they're not going to change. Not necessarily equal though. At this point, this is called the dynamic equilibrium. Concentrations are constant. So why is it called equilibrium? Something has to equal. That's why it has that equal piece in there. And that's this piece. Okay? So this is where two opposing physical or chemical changes occur at equal rates. Okay? So not necessarily the concentrations are equal, but the rates are equal. So the reactants are forming the products just as fast as the products forming the reactants. Okay? So this is equilibrium of rates, not concentrations. That is going to be your key thing. Now, this link here is to a video, which I'm going to play for you in just a second within this video. You need to make sure, do not concentrate on the actual kids or the voices or so forth in the video. You need to make sure that you concentrate on the concepts, because it goes back, it shows you what I mean about this.
We have right now 2 beakers of water.
Sorry.
And they look pretty much the same. They've got some nice blue food coloring into them. And I'm going to ask our lovely contestants here, one for you and one for you. They got these nice little cups. Now, you guys are going to bail. And what I mean by you're going to take a cup of liquid and take it out of your beaker, and you're going to put it in Carnisha's, and Carnisha's going to do the same thing back. Now, rules. No goaltending. Okay, you can't prevent the person from putting water in your beaker. Okay, and you want to get the water in the beaker, not at the beaker. You know, we're not looking to drown the classroom, okay? So, are you ready, ladies and gentlemen?
Wait, do I have to like dip it in there?
Yeah, you dip it in and you take a cup of water and you put it in his, okay? Are you ready, ladies and gentlemen? What do you think's going to happen?
Carnisha's gonna win.
Carnisha's going to win. Okay, ready. On your mark, bail.
Go, Carnisha.
I know, they're going pretty good. Look at them. Easy, guys.
Carnisha!
Easy. And bailing, not blasting. There we go. Bail. Yeah, they got a nice rhythm going there now. Look at that. Okay, stop. Oh, you guys are funny. So, they're madly bailing, and outside of the fact that some of the water is now on them, is there any much difference going on?
Not a lot.
Not a lot. I mean, Carnisha's bailing a cup out, and Jay is bailing a cup back. Should the amounts change at all?
No, a little bit.
Never. No, most of that's where Carnisha dumped it on the table, but that's okay. That happens. We allow for spillage. Now, I feel bad because Carnisha really is just driven to win. She's got this whole team cheering her on. So, Carnisha, I'm going to give you the big cup.
Okay.
Jay, you still got the little cup. Alrighty. On your mark, get set, bail. Yeah. In, not at now, guys. There you go. Whoa, what's happening now? Hey, no goaltending now. There you go.
You should just pick up the whole thing and dump it in
No, you can't pick it up. You can't touch the beaker. Okay. She's chunking up some water there. Keep going, Carnisha. Don't slow down. Well, that's okay. Splash him back. Okay, stop. Now, Jay, would you be so kind as to just hold your cup, empty it out, and hold it over your beaker? Carnisha, would you take a scoop of water and pour it into his cup, please? Pour it in his cup. Oh yeah, still got some room to go. Okay, now ready? Put your water in the beaker. Okay, start again. Go. Not
Did you just say
violently
ouch?
now.
Jason!
Jason, don't kill her.
Hey, she's black.
Okay, stop. Dump your water out, Jay, in your beaker. Okay, do the same thing, Kanisha.
What?
Take a cup of your water, pour it into his cup. It's a little hard, isn't it?
Yeah.
She's about filled his cup. Is any? Thank you, Kanisha. She's very insistent. Now, she's bailing out a small amount of water, and Jay is bailing back about the same amount of water. Is anything going to change?
No.
They've finally come to an equal rate. She can only bail out about half her cup, which happens to be about what Jay's cup holds. So the problem is, if she bails out her cup, Jay's going to put it back. Kanisha's going to bail it out, Jay's going to put it back. Is it ever going to be any different? The rate is now the same. So you guys have established equilibrium again. The rate is equal, so the amounts should stay constant. Are the amounts equal?
No.
No. They are constant. They're not going to get any bigger or smaller. They are constant, but definitely not equal. Okay, I really feel bad, Jay. You're trying so hard to empty your bucket, and Kanisha's just this vicious, double-fisted, big bailing person here. I'm going to give you 2 cups. So Jay's got 2 cups, Kanisha. You got 1. Alrighty? So what do you think's going to happen now?
Jay's gonna get really confused.
Jay's going to get really confused and start drinking the water. Okay.
Probably.
Alright, you guys ready? Okay.
Carnation's
Bail.
gonna turn into a lizard to eat Jay.
In, not at. Now take your time. There you go. Well, thank goodness this does not stain your hands or something. You guys have lovely blue hands. Not goaltending now, not. He's moving fast. Watch out, Katie. She's moving fast.
He has 2 cups.
I know, but you got a bigger one.
So?
They probably equal the same thing.
Oh, I heard somebody suggest it's going to equal the same thing. Would you stop?
You're so smart.
Okay, now Jay, would you hold your 2 cups over your beaker? Kanisha, would you fill your cup and then try and fill his 2 cups with it? She's getting every crumb of water she can. There's 1 cup, and there's the other cup. Is it ever going to change now? She's bailing out 2 cups, he's bailing in 2 cups. Notice the amount changed, but now it's staying constant. Once the rate is equal, the same amount comes and goes, the levels stay constant. Okay?
So now that you know what equilibrium means, we've got a couple more things to talk about. You have the equilibrium constant, which is called the Kc. Now, this constant, you're not necessarily going to be calculating. You just have to be able to know how you would find it if you were told to calculate it. So the thing that you've got to know is, suppose you had this chemical reaction where A, B, C, and D, the big letters, are the chemicals, and the little a, B, C, and D's are the coefficients. So these are your coefficients here, okay? The little numbers are your coefficients. All you have to do is you're going to do products over the reactants raised to their coefficients, okay? So products over reactants raised to their coefficients. So for example, you get big C raised to C, big D raised to D, divided by A raised to A, and B raised to B. Okay, so Kc is known as the equilibrium constant. It has a specific value at a specific temperature. So the only thing that can change the K is if T changes. Nothing else can change that constant. So let's do an example. So just using the alphabet here, 3A plus B produces 2C plus 3D. So the main thing you've got to remember is that it's products over reactants. So this means we're going to put C in the brackets because that means concentration, raised to the 2 times D raised to 3 divided by A raised to 3 times B. And that's it. That's all you have to be able to do for the equilibrium constant. So let's actually do a chemical reaction here. Now, these subscripts, remember, are part of the chemical. The only numbers that things are raised to is the coefficient out in front. So remember, it's products over reactants. So this means HI goes on top, raised to a 2, divided by H2. There's only a 1 there, there's nothing there, times I2. And that's all you've got to be able to do. Okay? So remember, products over reactants. Now, there is one last trick to this. And that's this slide. Okay? Substitute 1 for the concentrations of solids or liquids. So solids or liquids, we're going to put a 1 in its place, meaning they're pretty much going to disappear. You cannot change the concentration of a solid or liquid. Their concentrations are pure. So they're going to be a 1. So the only time you're going to include the actual chemical in your equilibrium constant is if it's a gas or an aqueous solution. So for example, we're just going to do the K just like we've been doing this whole time so far. So remember, it's going to be products over reactants. So we're going to do CO2 times CaO, okay, divided by CaCO3. And they all have 1s in front, so that doesn't matter. Now, if they were all gases and aqueous, that would be our answer. But, as you can tell, remember these right here tell you the state of it. So CaO is a solid and CaCO3 is a solid. So what happens is CO2 stays there, but CaO becomes a 1 and CaCO3 becomes a 1. So since they're 1s, your actual final answer is simply CO2. Okay? So the only thing that should be in your equilibrium constant equation is if it's gas or aqueous. Now, what do these K values mean is the next piece. Why do we care about this K? And that's this slide. If K equals 1, meaning, now it all comes back to this here. It all comes back to it being products over reactants. Okay? So if K equals 1, this means, what about this fraction? How does a fraction equal 1? So, for instance, if you had 2 divided by 2, that would equal 1. So this means that P has to equal R. That's the only way a fraction can equal 1. So there are roughly equal concentrations of products and reactants at equilibrium. So they're going to be the same. So then what if K is greater than 1? So how do you get a fraction to be greater than 1? What number has to be bigger for this fraction to be greater than 1? Well, the top has to be greater than the bottom, right? In order for a fraction to be bigger than 1, the top has to be bigger. So for instance, 4 divided by 2 is greater than 1. The top has to be bigger. So products exceed the reactants at equilibrium. The products are going to be there's going to be more products than there are reactants. Now if the Kc is a lot greater than 1, this means that the reaction goes to almost completion, meaning you have hardly any reactants left and you're mostly at your products. If K is less than 1, this means, looking back at this fraction again, what number has to be bigger? This time, your reactants have to be greater than your products. So your reactants are going to exceed your products. And if K is is extremely lower than 1, this means it barely proceeds, meaning it hardly does anything to react. Okay? So this is the purpose of that Kc and being able to calculate it and so forth. Now, we're not going to actually put any numbers into it. You just have to be able to tell me the equation. Okay?